Really elegant little vector question. Important thing is that you read it carefully and draw things on your diagram. Position vector of A is A, so therefore that if you go from O to A, you are doing A, and it's hard to draw bold. Don't worry about that as long as you've got the vector in there or the arrow in there. And we know that the position vector of C is C, so therefore going from O to C, I'll get a C. Rubbish bolding, but never mind. Now, first thing I want, my first question, what have I got? I've got a 2 to 1 on this thing here, so that's 2/3. And this one here is the midpoint, so therefore it's a half. And because it's a parallelogram, we know that in parallelograms, opposite sides are the same length and they've got exactly the same gradient. So therefore, if this side here is A, this distance here will be 2/3 of A because it's exactly the same length. Well, C to B is the same length as A, so therefore it would also be the vector A, and C to E is 2/3 of A, and the side AB is parallel to OC, so therefore AB is also the vector C, but A to D is a half of C. So what I've done is I've actually put a lot of my information onto my question. So I want the vector AC. So if I want to go from A to C, that way, my clear route, and I'll stick with what I've got, so my vector AC, and it's not a bad idea, okay, it's only worth 1 mark, but in terms of clearness, I'm going to go from A to O, and then follow it with O to C. Now, a thing to remember with vectors is that if you go against them, they get very upset. It will be negative. So it's minus A going in the opposite direction. The negative tells you the direction that you're going in, plus C. And as a mathematician, I would be tempted to write that as C minus A. There's my first answer. The position vector of D, well, if I want the position vector of D, I'm talking about actually the OD vector. So if I want to go from O to D, I've got lots of different ways of doing it. Always choose the shortest route. Okay, so I'm going to go from O to A, and then follow that by A to D. And you can see on my diagram that I've already put in most of what I need. A plus a half of C. That would do. You could tidy that up a bit if you wanted to, but it's not really necessary. And my third part, which is the position vector of E. Now remember what I was saying, that this is the vector OE. And I will put this one in. Didn't put the other one in because it's getting a little bit cluttered. This is my vector OE that I'm looking for, and that gives me my position of E. And going from O to E, I could, if I really wanted to, go O to A to B, and then B to E, but that'd be really silly because I've just marked on that I've got 2/3 of A, and we'll clarify why that's 2/3 of A in a minute. Okay, so this is going to be OC plus CE, followed by CE because the addition means that. So therefore this is going to be C plus 2/3 of A. And some people would say, well, you've got to bold these, or you've got to put a bar on them, or a squiggle. It's clear that I know what I'm doing here, but my diagram helps. Let's just clarify this 2-to-1 ratio. 2-to-1 ratio means that I've got a length, it doesn't matter what it is, and it's split. So this is 2 parts, and that's 1 part. So clearly the line is split into 2 plus 1 parts, and 2 plus 1 gives me 3. So therefore this bit is 2/3 of my line, that bit's 1/3 of my line. No real problem. Now, so this question, or this part of the question, worth 2 marks, so I've got to do a little bit of work for it. But I've got to show my reason, so I've got to do something and a reason. And I'm looking to see whether it's parallel or not. Okay, now if it's parallel, what I know is that my vector DE must be some multiple of my vector AC. And in this case, looking at my diagram, and I'll redraw the diagram in a minute, K is less than 1. It's a fraction. I know that, but so if I want to use that method, I've got to find the vector DE, so I need a quick diagram, and artistry is not my forte, but never mind. That'll do as my DE line. Here's my AC line. And so I need to find DE. So I had in my answers to the previous parts that OD, or the position vector of D if you like, was A plus 1/2 of C, and that OE was C plus 2/3 of A, and if I want to go D to E, I need to go D to E is going to be D to O, which is the same as OD but in the opposite direction, plus O to E. So I'm going to get minus A plus 1/2 C. Don't really need the bracket there, but I put it there just because I want to distribute the negative sign, plus C plus 2/3 of A. So I've got minus A minus 1/2 C plus C plus 2/3 of A. So I've got minus A plus 2/3 of A, which is minus 1/3 of A. And I've got C minus 1/2 C, which is plus 1/2 C. And that's not a multiple of A minus C because the fractions are different. Therefore, they're not parallel. Okay, you would need to write that in words. The other one you could use, which you might consider here, which I quite like, is that the fact that the triangles are similar. Okay, that you've got, in this particular case, the triangles are not similar because that's 1/3 of A. This is 1/2 of C, but that angle at B, whatever it happens to be, is the same. The other one this side here is A, that side there is C, that angle there is still alpha. I suppose I should put the letters in. And they're not similar, they're not congruent, or they're not similar triangles. So you could say that they weren't similar because the ratios aren't the same. Okay, so therefore we could go for non-parallel for the same reasons. Again, you'd have to write that down.
Just going to have a quick look at this question on Geogebra, and just to mention that Geogebra has lots of functionality for vectors, and for those of you who've come across them, also for matrices. So the point of showing you this is to show you that vectors are a very flexible tool. The picture on the screen looks a bit like the diagram in the exam question, with a few additions following through the question. So we can see the line from A to C and from D to E as in part B, and we can see that they're not parallel. And they're not parallel for this A, and that should be bold, but never mind. That is A the vector, that is C the vector. But what about if we change A or C? Well, the thing about vectors is that you get generalized results, and that makes it in some respects a more flexible tool than coordinate geometry. So if we do move this point A, which is used to define the vector little a, then we can see that, sure enough, the green line and the red line are not parallel. We can also see on here, incidentally, that the other method of showing that they're not parallel, which was the similar or non-similar triangles BDE and BAC, we can see that they stay non-similar whatever we do with A or with C. It may look like we're getting close to being parallel, but in fact we're not. So, as I say, one of the beauties of vectors is that we can find results and then we can apply them to a whole family of basic vectors or basic vectors defined by points, and the results will still hold. And so if we had some sort of situation where A and C were changing dynamically or over time, and we needed to know whether these two lines ever became parallel, then we can just show it using vectors in this way, which reduces calculation and so on.